Hello and welcome to this review tutorial lecture for Further Integration Chapter 4. So if you look at the previous questions in previous years, there is a bit of a pattern, and as far as I know it persists for your one. So question A is going to be either an antiderivative or an integral. Antiderivative or an integral. Part B is usually going to be find the work done by force. So you have to do, the work is the integral of force. And question C, usually, well, pretty much always, is either the centroid of a lamina or center of gravity 3D. Now that's not so much a hint so much as the paper I wrote for you is pretty typical, and if you look at previous years this is what you'll see. Okay. Now we have, remember we have our strategy for anti-differentiating. If we want to calculate any integrals we need to do anti-differentiation, and the strategy that I've recommended is first you try and do it directly using tables, do an antiderivative. If that doesn't work you need a manipulation. If that doesn't work you need a substitution, and if that doesn't work you need to use parts. Now what's new in this module versus what you've seen before is integration by parts and a special manipulation of complete the square. And the odds are both of these are going to be in your question. Now the parts can come in here, it's kind of hard for me to get complete the square in here, so usually it's not going to be there. The usual situation is there's no integration by parts here. There might be, but usually there isn't. But usually both of these between them will have a parts and a complete the square. So if that might be parts, that might be complete the square, or that might be complete the square and that might be parts. But any possible integration technique can actually arise here. Okay, right, let's go through. Now the whole time remember what we're doing is when we answer our question we'll have half an hour to do this question 4, which will be an assessment for us. We will have time to say, have I answered the question that's asked, and does my answer make sense? Okay, so what we're confronted with here first of all is t antiderivative. Now that's good because you've no integration, no limits to sub in. We're asked to find this. Okay, so you can say, oh, be prepared for integration by parts and assume this is integration by parts. Now that would be good as long as it doesn't need integration by parts, in which case you've probably made it harder than it needs to be. So even though you're suspecting integration by parts, you should say, what about the tables? Now it's not going to be in the tables because they're multiplied together. You can't do it term by term, so that's gone. Manipulation, there's nothing really here you can do to rewrite it. Substitution, you could try w equal to minus 2t, but if you carry that through it doesn't make it any bit easier, which suggests that you're going to need parts. Okay, so what you do at that point on the question paper, the integration by parts formula will be written. It says antiderivative u dv is equal to u by v minus v du. So we've decided it needs parts. Okay, so you pick the u according to the at. So you say any logs here? No. Any inverse trig? No. Algebraic? Yes. Now if you look at the u, it multiplies. So although this is an algebraic just means sums of powers of x, in this case sums of powers of t, the u is not inside something else, so this is going to be the u. Okay, so we'll say that u equal to t. I'm going to just call this thing I for my own notation, and let's start writing down what I is. So I, using this formula, is u by v, u is t. Okay, now we have to find what v is. So the way it works is you pick your u and then everything else is your dv. So all of this is dv. So I have dv is equal to e to the minus 2t dt. Okay, now how do you get from dv to v? This will be discussed in the integration by parts lectures. You anti-differentiate, or really I should probably say here, integrate both sides. V is the antiderivative of e to the minus 2t dt. Now we're confronted with an antiderivative. This is our strategy. So first we go to the tables, and this is in the tables. So this is like e to the ax, and the antiderivative e to the x is 1 over a. Here the a, the multiple of x, in this case t, is minus 2, e to the minus 2t. Okay, so that's our v. So if u, v, this is v, minus integral, using this formula here, v, which is still 1 over minus 2 e to the minus 2t times du. Now if u is equal to t, then du and dt will be the same, but we'll just show you how it goes. So you differentiate both sides here, du dt. So if you got u and you want to get du, you need to differentiate. So du dt, the derivative of t respect to t is 1. Multiply both sides, nonsense but gives you the right answer. Du is equal to 1 dt, which is equal to dt. So that's us using the formula. Okay, now what are we going to do? Well, what I'm going to do here is, this is plus divided by minus, which is minus. So I have plus by minus by plus. Now it doesn't matter about the negative exponential, that thing is still plus. So plus by plus is minus. For no big particular reason, I'm going to fix the half. And then I've got t e to the minus 2t. And then what we have here is minus times minus a half is plus a half. Antiderivative e to the minus 2t dt. Okay, and now what we can do is we've another antiderivative to do. It's in the tables. It's the first thing on this list. So we get that our antiderivative is minus a half t times e to the minus 2t plus a half. Antiderivative of this is 1 over minus 2 e to the minus 2t. Now we could tidy this up and turn it into a minus a quarter, but I'm not too bothered. But for full marks, maybe we'll tidy it up. It's kind of bugging me a little bit there actually. So we'll do minus, now if you do plus c, or we'll get full marks, but minus a half t e to the minus 2t. A half by minus half is a minus a quarter, e to the minus 2t, and for full marks plus c. If it's an integral with limits, you'll substitute top limit minus bottom limit, but this is just an antiderivative. If looking for all antiderivatives, you must also do plus c. Have you answered the question I was asked? Yes, we have. We have found this antiderivative. And then, does your answer make sense? In this assessment, I would say that after you do the 3 parts, you could check your answer by differentiating this. Now this will just need a little product rule, but you can check your answer here. So that's good. I won't do it here. Okay, second question. So this is from page 226. A force in kilonewtons acting on an object is described by, well, there's a formula for the force here, where x is the displacement of the object from a point O. Show carefully that the antiderivative of this force, and it kind of goes through, is it 1/3 tan inverse x plus 2 over 3 plus c. So this question is nice in that it's essentially a work question, but it's actually giving you the answer for the antiderivative if you can't do it. Okay. Well, let us have a look at it. Okay, so part 1. So we're asked to show something. Now, if you're very smart here, so the 1/3 inverse tan x plus 2 over 3 plus c, you could cheat and you could differentiate the right hand side. And if you got 1 over x squared plus 4x plus 13, well, that'd be the question done. I mean, it's trying to show the antiderivative of that is that. If you show that the derivative of that 1/3 inverse tan thing is the thing on the left hand side, you'd be done. Now, of course, the thing is, we won't assume that here because maybe the answer probably isn't on the page in front of you. So we're looking at 1 over x squared plus 4x plus 13. So this is, you will see that this is a complete the square question. If you, as we discussed in the lectures around this section, if I was just to throw this at you, it'd be a little bit difficult. You want to kind of be thinking, oh, complete the square is in there somehow. It's a little bit difficult. I mean, you look at it, it's not in the tables, but actually if you kind of look in the tables, there's something similar to it. And that can set you on your way. So the closest thing to that is 1 over a squared plus x squared, if you're looking in the tables. After that, you're thinking of manipulation. Now we've got this special manipulation of complete the square, and we will do that now in a second. If you try and do a substitution, you're going nowhere, because you don't have a function multiple derivative, and parts isn't going anywhere. It's a special manipulation, complete the square. So what we have to do, I'll keep this thing here. What we have to do is kind of force x squared plus 4x plus 13 force it to look like a squared plus x squared, but in the language that you'll learn about if you went to level 7, except that x is shifted to x plus b. So this is shifting. And doing this is what we call completing the square. Now some people can do this in their head. I mean, you might see that b has to equal 2, and you're not too far away then. But if you can't do it in your head, as most of us can't, multiply this out. Now if you carefully multiply this out, and I'm going to write it in a different order, I'm going to do this one first. So x plus b by x plus b, carefully multiply x plus b by x plus b, x by x is x squared. You get b by x and x by b, both of them are bx, so there's plus 2bx. Any questions about anything, you can email me, and you also b by b is b squared. So that's the x plus b all squared, and there's also an a squared lying about. Now you're trying to force this to equal this does equal this, so you're trying to force these two things to be equal to each other. Now what they have in common is this x squared. That's good. And now let's see what else we have. Well, how many x's over here? Now you say something not great, like, oh, there's one x, or oh, there's two x's, or three x's. What I mean is, what is the coefficient of x, what is the multiple of x? And over here, what is the multiple of x to be? So I want those two to be equal to each other. So I'm going to force 2b to be equal to 4, and to solve for b, I divide both sides by 2. b is equal to 4 divided by 2, which is 2. Okay, similar story. The constant over here is 13, and the constant over here is b squared plus a squared. So I want b squared plus a squared to equal 13. I already know that b is 2, so b squared is 4. I can take away the 4 from both sides. A squared is equal to 9. I want to get a on its own, the square is in the way, so I do the square root of both sides. We would have discussed at length, and it's important for example, perhaps parametric differentiation or even implicit differentiation, that you understand that this has two solutions. So there's a plus and minus situation here. You can take the negative one, but please don't, just take the positive one. Forget about the negative one. It's not wrong, but you don't need it. Plus square root of 9 plus square root of 9 is 3. So what we've managed to do is, again, if I call this thing I, it's nice for my notation, rather than having to write all this out again, I can just refer to I. The antiderivative that I'm looking at, 1 over the x squared plus 4x plus 13. Well, if a is equal to 3 and b is equal to 2, it's actually 1 over this is 1 over this with the appropriate values of a and b. So the a is 3 and the b is 2. Yeah, dx. Now you can, if you're not careful, you can kind of just use this formula here, but it's not a good idea, in my opinion. It's just not great maths. You get away with it if you do the... Okay, so what is this? Well, you look in the tables, you see the 1 over a inverse tan x over a. If you just apply this formula now, you will get the answer in the notes. My concern is that you can't apply that formula if you say 2x here, which you probably won't get, but look, we'll try and do things properly. This is not exactly of this form, so I want to do a substitution. And if you can do all that, you can see that this is the substitution. Although I suppose if you could do all this, you might be, yeah, this is the substitution. So you get 1 over 3 squared plus, we're going to let w equal x plus 2. Okay, so this is now w squared. Now what I want to do is I want to replace the dx in terms of the w, and to get a relationship between dx and dw, I differentiate w. So dw dx is equal to 1, and you see what it is, dx and dw are the same. If this was a 2, this would be a 2, and then you couldn't use the formula directly, but here it's okay as long as that multiple of x is 1. So you get dw is equal to dx, in other words dx is the same as dw, dx is the same as dw, and now this is exactly the correct form. I can use that tables, so 1 over a, the a is 3, inverse tan w over 3. Now that isn't the full answer because we're asked to anti-differentiate with respect to x, so we should go back in terms of x. In other words, put w equal to x plus 2. And, well, you won't forget about the plus c when it's written on the paper, I guess. Okay, so that's part 1 to show this. Second part of the question is, the object is moved by the force, and this here, this is the force from O, which is distance 0 from O, to a point 1 from O. So let's see what we're going to do here. So basically, if I draw a little picture of what's going on, x in this picture is the distance from O, and this, okay, so in particular O is a distance 0 from itself, and we're going from here to here. So the work done will be the integral, and this thing that, oh, the work is the integral of force, that will be on the question paper as well. So to find the work done, you integrate the force from 0 to 1. Indeed, if this was going, say, from 0 to 10, you integrate from 0 to 10, whatever it may be. So we write work here is the integral from 0 to 1 of the force. The force is this yoke, this bit that's written in the question, dx. Now the good news is we've done all the hard work. It's very easy from here. You get marks for writing this down, and then, well, how do you calculate an integral? You do the antiderivative. Well, we've just done the antiderivative in the previous part, and of course this is an integral, we don't need the plus c. If you throw it in, it's not wrong, it'll just kind of cancel out. So you get this is equal to 1/3 inverse tan, this is from here, and of course you could do this if you couldn't do it, because the answer is on the page, you can still do the second part even if you couldn't get the first part. So now we're going to do top limit minus bottom limit. This will be one of those scenarios where the 0 does not give you a 0, to be a bit more careful. And I would also say that you have to be in radians. Okay, so we get 1/3 inverse tan, so in the top limit, 1 plus 2 over 3. So that's substituting the top limit, minus substituting the bottom limit. This is 0. And I think there's clever ways of adding those together, but we're just going to use a calculator. In radians, 1/3 inverse tan of 1 is 45 degrees, minus inverse tan of 2/3. I'll round this to 4 significant figures. So I get like 0, 6, 5, 7, 9, 8. So rounding to the significant figures, it's asking for 3 significant figures. That's great. So 0.0, that's not significant. And I have 6, 5, 7. But the 7 is followed by a 9, so that should round up to 8. And now you want to think about units. The units of the force is kilonewtons. The units of the distance is meters, so it is kilonewton meters. If you want to turn it into kilojoules, that's fine. I think it's equal to 65.8 joules, but yeah, whatever. That's that question. So you might have to do an integration by parts here. You might actually just need a substitution here. I suppose time will tell. And now we're on to the final question. So the final question, it's either going to be a centroid of a lamina or a centre of gravity of a volume of revolution. Oh, I said I'll leave this. Okay, so part C. So consider the lamina. So it's two-dimensional. I don't know which one is easier.